Morning, everyone, and it's a pleasure to have Dr. Dhiman Bhowmick as today's speaker for our department. But I do find actually very pleasantly surprised. Actually, there are many other in the audience who are outside of our department. That just tells you, the importance of your work. So Dhiman is currently in NTU in Singapore and working with Pinaki Sengupta, I know very well. And you did your PhD in IIT Kharagpur.
No, no, under Pinaki, I'm currently continuing.
Doing your PhD with Pinaki?
Yeah.
So you had a
IIT Kharagpur, I did my master's.
your masters because I found one publication there with Professor Shamit Ray, who was a director here. So Pinaki's expertise is on quantum magnetism, and today in particular he is going to talk about topological edge magnons, which is one of the current field of interest. So
good morning, everyone, and thanks, Prof. Tanushree, for this nice introduction, and thanks to all for giving me this opportunity to present my work, one of my works. So today I'm going to present my work on the time crystal, which is I proposed a time crystal based on topological edge magnons. And this work I have done with the collaborators Dr. Sunhao, Professor Yango, and Professor Pinaki Sengupta, who is my current guide or mentor. And this work is published in this archive. So without any further delay, I am starting my talk, giving first the overview. So I have kept my talk in such a way that most of the jargons that I'll be using, I will try to introduce in first three sections, which is I will introduce the time crystal first, then I'll introduce the topology with brief two slides, and then I'll jump into introduction to magnons. Then at the end, I will talk about my main results. And that main result I have divided in three subsections. One is time crystal via parametric amplification. Second is the stability of the time crystal, and the conclusion. So first part is introduction to the time crystal. So before understanding the time crystal, we need to have a background knowledge what is a space crystal. So even the space crystal, the system has some periodicity, but the Hamiltonian of the system, which consists of momentums and the interaction among the nucleus and the electron, it does not show any periodicity. This Hamiltonian is invariant under translational symmetry. So if I translate this Hamiltonian in the space to other point, it will still be invariant. So one might expect the system should be also invariant translationally, but it is not the case. But the translation symmetry is will be spontaneously broken if somebody makes a measurement of one position, and if one makes a measurement of a position of one of the nucleus in the system, the conditional probability of getting another nucleus will already be fixed and it will have a periodic structure, and that is due to the interaction among the particles. And this conditional probability will be periodic is because of the interaction among the particles. So we can get a space crystal in such a way, but what is the how is this space crystal? How much is this space crystal is stable? Means when it decays. So one of the greatest minds, Einstein, was baffled by this by the weird quantum mechanical laws, and he asked a question that why so if we observe the moon, does it means if we don't observe the moon, does it mean the moon is not there? He was baffled by the question that because wave function collapse, and after wave function collapses, it will again spread and creates the another wave function. So one might say that if we don't see the moon, then moon might be not there, because it will have again a quantum mechanical wave function. But the answer is in the mass of the moon. The mass of the moon is very high. And so once the space crystal is created, because the space crystal is very highly massive, the space crystal still continue to be of the structure, and we can see it qualitatively from the by arguing using the uncertainty principle. Let's say the space crystal, all the atoms in the space crystal has an accuracy of delta x to the minus 11 meter. Then from the uncertainty principle, one can derive the momentum, and for 1 kg of that substance, the velocity should be 10 to the minus 22 meter per second. And the time to delocalize that center of mass of the system uh, with the length scale, within a length scale of 10 to the minus 10 meter, which is a lattice constant of the crystal, then it takes around 10 to the power 4 years. So thus the space crystal is highly stable. And so these are the two slides to introduce the space crystal. Then I will carry on this concept of space crystal into the time crystal. So first, Nobel laureate Frank Wilczek asked this question, that can we realize a time crystal in the time dimension instead of the space dimension? So the picture he thought is about like this. So if we have a system at time t, the state of the system will periodically change, and it will again come back to t plus t, and it will form a time crystal. And so can you realize this time crystal? So first, Frank Wilczek showed that time crystal can be realized in the ground state of the system. But later on, for a decade over, there are many various papers were published, and there are many debates. And at the end, they found that there is a no-go theorem. The time crystal cannot be realized in the ground state of the system for with a few body interaction, maybe 2 body or 3 body or 4 body interaction. It cannot be realized. So one requires the system to be in the excited state, and so because one need to maintain that excited state, the stability of the time crystal is lower than the space crystal, but there are many stabilization schemes to stabilize that. Before jumping into stability, first let me ask a very yeah.
So when you showed your first slide on time crystal, is time translation symmetry breaking, right?
Yeah.
So can you quickly tell me what the difference between an oscillator, because oscillator will also have this property.
That is what I'm going to answer. That. So the thing is that one may think about that time crystal might be a pendulum, but it is not the case. The pendulum is not a time crystal. It is because pendulum's oscillation is not intrinsic to the system. Instead, the period of the pendulum is depends on the gravitational constant g, and it depends on the gravitational field, as well as the stability of the pendulum is not very robust, because if we have an external force with different oscillational frequency, the pendulum will start to vibrate with that frequency. So these are the two reasons that a pendulum is not a time crystal, because it does not have an intrinsic frequency is not intrinsic to the pendulum, the system, and also the stability is not that robust. So to stabilize a time crystal in quantum mechanical system, there are various schemes, because we need to keep the system into excited state. We need to stabilize it. So there are mostly 3 proposed schemes. First is the MBL, or many body localized state. Second is the pre-thermal state, and third is the driven reciprocity. And this many body localized state is a very interesting phenomenon, where the excited state does not follow any statistical mechanics, the conventional statistical mechanics. So, for example, let's say I have a ice cream made of, let's say, many body localized ice cream, and that I kept in refrigerator and take it out of the refrigerator at 40 degrees Celsius. It will still be remain in that many body localized state without any interacting with the environment. So it is robust. It does not interact with the environment. So we can use that many body localized state to create a time crystal. And also there is another scheme which is pre-thermal scheme. This pre-thermal scheme is quite analogous to the scheme of the space crystal. The space crystal was stable is because it is very massive. And this pre-thermal scheme is analogous because if we create a time crystal out of Bose-Einstein condensate where we have macroscopic number of particles in the system, then it will take a very long time to decay. So we can create time crystal using Bose-Einstein condensate that will be a pre-thermal kind of time crystal. And the last scheme is the driven dissipative one, where if we drive the system and the driving rate of the system and the dissipation rate of the system is equal to each other, then the system will never decay. It will remain in the one of the steady state. So we get a time crystal out of this way, and this is called driven dissipative mechanism. So time crystal, yeah.
Sorry, a question. Can pendulum be not
No, the frequency still need to be in the intrinsic to the system.
But what
That's
about
correct.
two masses connected to the screen?
Yeah.
It still depends on the gravitational constant.
Two masses empty in space, given by a screen, connected by a screen. If you press it, it will oscillate.
Okay. So the thing is that
I think the
Okay.
key thing is in the ground state.
Yeah.
Ground state, when it oscillates, it has involved excited states. That you cannot happen.
that is a classical thing
Yeah,
actually.
so even you can make it quantum. That's not
Yeah.
a problem.
You can
But
make it a quantum,
yeah.
but the whole idea and the philosophy actually fits something. I mean, that's my view.
so for ground state, I think this property that you're talking about, that it has must have this period, it must be only purely when it occupies the ground state. It cannot have any component from the excited state. If it has components from even the harmonic oscillator, which is components from excited state, it will have oscillating interval.
The thing is that in case of classical states, one can realize.
I'm talking about quantum. Take
Quantum.
a quantum harmonic oscillator, populate two states, ground state and the excited state.
Yeah.
You will have quantities that change in time,
Yes, yes.
right? So we cannot call that a time crystal.
And also, it need to be robust against the external perturbation.
Well, fine. So if I define external perturbation here as changing omega, giving some noise in omega, it will be kind of low. I think the main point is that there's a ground state.
No, it is not possible. In quantum mechanics, the ground state cannot give a time crystal.
For if you are breaking continuous time translation symmetry, it cannot. But if you are breaking discrete time translation symmetry, it can. Wilczek's paper said it has to break continuous time translation symmetry. That
Yes.
is true. You cannot have that.
Yeah.
But then what this Vedika Kemani special only these people did,
Yeah.
they broke discrete time translation symmetry.
Yeah, but that discrete time translation symmetry is exciting, right? It's an external field that
But
is.
even then, so basically you have Fluke Hamiltonian.
Yeah, that is
Ground
a,
state of still the ground state of the Fluke Hamiltonian. There is some notion of ground state even in that case, in the periodically driven system.
I think this needs
Yeah,
longer
yeah, I
discussion.
think, yeah, please continue,
So
sorry.
please continue.
Yeah.
So the time crystal also can be categorized into two kind of system. One is the continuous time crystal, and there is a discrete time crystal. This continuous time crystal breaks the so the time crystal breaks the continuous symmetry, translation symmetry. Then it becomes a continuous time crystal. But if it breaks a discrete time translation symmetry, let's say I have an external drive which has some frequency, but the time crystal is breaking that period of oscillation, and have its own internal kind of period, and that breaking gives a discrete time crystal, breaking of discrete time crystal symmetry, and that gives a discrete time crystal. And after introducing to the time crystal, I am jumping into the introduction to the topology. And this topology I kept in very brief 2 slides, where the first slide I described the topology in terms of 2-dimensional manifold embedded in 3-dimensional space, where I have given 3 figures here. The 2-dimensional manifold is a sphere, and the second is a torus, and third is a coffee mug, where these numbers here are the Euler characteristics. You can see that the Euler characteristic of coffee mug and the torus is the same, whereas this sphere is different. So it means that torus and coffee mug has the same topology. So what does it mean is that we can deform this coffee mug into this torus without tearing apart the surface. Or you can say that if we there is an adiabatic transition or adiabatic deformation from this coffee mug to torus. But from sphere to torus, we need to tear apart the surface, nearby surface point, and that is a non-adiabatic process, and so they are topologically non-equivalent to each other. And so this concept also applicable in various fields, and in condensed matter theory we have the band topological systems. And so what in this case the manifold is constructed by the states of the system in the Hilbert space, and we study the topology of that Hilbert space. And so this non-adiabatic transition that I have mentioned, to deform from one topology to another topology, we need to close the band gap and then again reopen, and so the topology changes from one topology to another topology. And another interesting phenomena that is this we can find in the topological system is the boundary states of the edge states, and this is because of the boundary that separates the vacuum from the topological system. The topological system has a non-trivial Chern number, whereas Chern number or maybe other topological number, and that separates the vacuum state. Vacuum state has a trivial topology, and so there should be a non-adiabatic transition at the boundary, and the gap should be closed, and we get gapless states at the boundary. So there are various kind of states possible, like for example, chiral state, helical state, Fermi arcs, and higher order topological states, and so on. So in this discussion, I have some chiral states in my study. So so that is the introduction for topology in condensed matter system. And let me introduce the magnons. So before introducing the magnons, I need to talk about what are the spin waves. The spin wave is made of, first I am introducing ferromagnetic chain, where the electrons, the charge of the electrons is neglected, charge degrees of freedom, because electrons do not hop from one side to another side and give a current. So one can consider only the spin degrees of freedom, and these spins align with each other and gives us a ferromagnetic ground state. One might think that one tilted spin is the excited state of the system, but it is not the case. But we have a state made of many tilted spins, such a way that if we join the arrow head of different sides, we get a spin wave. And in quantum mechanics, this spin wave or this eigenmodes translate into bosonic operators. So here I have this eigenmodes, the corresponding bosonic operator is given by AK, and this can be written down in terms of the superposition of the many operators in the real space, which are AI cap, and these are known to be constant Cherenkov operators. And this in linear spin wave theory, we can easily write down the relationship between the spins and the Hall-Cherenkov operator is very easy. Like the SI plus cap is related to AI cap, SI minus cap is AI cap dagger, SI is the related to the number operator in the Hall-Cherenkov operator. So this I have ended introducing all the important things, the time crystal topology and the magnons. Let me jump into my own work, that is the main result. And first I am talking about the time crystal via parametric amplification. So I have a system Hamiltonian, which is a Heisenberg exchange Hamiltonian, which is a ferromagnetic Heisenberg exchange Hamiltonian. So if we think of this Hamiltonian classically, then all the spin must align with each other, which is where I have considered only nearest neighbor interaction. So SI is a spin at ith side, and Sj is the spin at nearest side j to the ith side. So and classically, if we think, then all the spin need to be aligned with each other to give to minimize this energy. And so that is what is described here is a ferromagnetic ground state on a kagome lattice. And moreover, what I have done, I have added external electromagnetic field to drive the system. And this Hamiltonian consists of this electric field, where E vector is the electric field amplitude, omega is the frequency of the electric field, and Pij vector is the uh, mm, polarization operator, which depends both on spins of the system. And so the briefly, I can say that if I drive the system using the external magnetic electromagnetic field, use it with a period t, then the edge spins will oscillate with a period of 2t, breaking the discrete time transitional symmetry, which is given by this external electromagnetic field. And how it is done, I am going into details now. First, the unperturbed system. So unperturbed system has the electromagnetic field 0. It means the ground state still remains ferromagnetic ground state, and we can use the Hausten-Krampf transformation and can change this spin Hamiltonian that I have described here in terms of the Hausten-Krampf operators. And because this is a non-iterating system, this can be easily diagonalized, and we can get the eigenstates, and we get the band structure in the K space, and one can see these modes here in between two band structure, and this is in between third and second band structure. So these modes are due to the topological pi verifice of the bulk bands, and so these are topological edge states here, and mm, so the Parta system that I have introduced an extra electromagnetic field that couples with the polarization operators of the system, and this term we can simplify more using the rotating wave approximation, where we neglect the higher or higher frequency term, higher order oscillation term. So we can make this Hamiltonian independent of the time in the rotating frame, and the interaction Hamiltonian surprisingly gives this kind of term, where this first term is the pair creation term and the second term is the pair annihilation term. So what does it say? The physical process that give rise from this process is depicted in this picture. So the system absorbs one of the photon and gives two magnons out of it, pair of two magnons. So this is the pair creation process. So we can use this pair creation process and can amplify the magnons if the dissipation of the system is less than some electric field amplitude. So if the process of pair creation dominates over the process of damping, which happens when the electric amplitude is greater than gamma square by 4, where the gamma is the damping of the system, and then it creates two pair of magnons with this energy conservation laws. Omega k plus omega minus k equals to big omega. Big omega is the frequency of the light, and omega k, small omega k and small omega minus k is the frequency of the magnon. And so I have shown that we after introducing the interaction, I have this pair creation term, and introducing this pair creation term, we get another Hamiltonian, and we can diagonalize this Hamiltonian using Bogoliubov transformation. And after diagonalization, we get the eigen spectrum to be complex. Why it is complex? The imaginary part is introduced because there is damping, and secondly, there is this electric field that is giving rise to the amplification. So we get also the imaginary part. And if this imaginary part is positive, then we get amplification. And here I have plotted only the real part of the eigenspectrum in this black line, in terms of these black lines, and only the yellow dots here are eigenspace uh, which are amplified, means the imaginary part of this eigenspectrum is positive. And so what is the consequence of this amplification? So when the electromagnetic field amplifies this, then the number of magnons increases, and this number of magnons is proportional to the SZ component of the spin at the edge. So the SZ component remains constant, whereas the Sx component is proportional to this field of the magnons. So, and this field of the magnons is proportional to this part, which is e to the power I omega by 2 by t. So the oscillation that is happening in the Sx component is half of the frequency of this external electromagnetic wave, and that is what I have shown here. So this Sx component for up state and down state is oscillating, and this is the magnified picture of this. And second section is stability of this time crystal. So discussing about stability, I need to discuss first the symmetry of the system, because this time crystal is protected by it need to have time crystal symmetry intrinsically before giving rise to time crystal. But in many spin systems, there is one symmetry is lacking, is that is the time reversal symmetry. If time reversal symmetry is broken, then the translation symmetry is already broken, and so the system cannot give rise to time crystal. And this time reversal symmetry is broken by the Dilution-Moria interaction. And we can see that if we introduce this Dilution-Moria interaction, then this dispersion here changes. And before the two edge states were overlapping with each other, but now the states near k equals pi are crossing with each other.
So to have a game interaction,
Yeah.
you need to have a non-central symmetric crystal.
Yes, correct.
So that means already in the crystal, the inversion symmetry is broken.
Yes, yeah.
So that has a consequence with the, because you are connecting it to the time reversal symmetry.
Yeah, correct.
But the Zalizensky-Moria is connected also to taking of
Inverse symmetry, correct, yeah. So
which symmetry you are talking about?
So firstly, the crystal breaks inversion symmetry. It gives Dilution-Moria interaction, and this time reversal symmetry what I am talking about is in terms of magnons. So in the magnon Hamiltonian, it breaks the time reversal symmetry. But if we talk about in terms of spins, then if the inversion symmetry is broken, there is Dilution-Moria interaction. So
if I understand correctly, since you're talking about ordered, spin ordered system, your time reversal symmetry is broken to start with.
Yeah.
Right.
I was
Because
also wondering.
spins are ordered, right?
no, the thing is that this time reversal symmetry is an effective time reversal
He is
symmetry.
talking probably at the magnons.
So in the you're saying in the magnon sector, you
Yeah,
have
magnon
some
sector.
remnant of time reversal symmetry.
No, the thing is that this is for, if I make it more precise, this is effective time reversal symmetry. And this effective time reversal symmetry you can get in the paper of interaction-induced topological magnons. So this is not the actual time reversal symmetry. Actually, I did not mention it so that to make it more simpler.
Okay.
So this is an effective time reversal symmetry. And this time reversal symmetry is a time reversal symmetry multiplied a spin rotation operator. So that is an effective time reversal symmetry that needs to be preserved. And so if that effective time reversal symmetry is broken using a Dilution-Moria interaction, even not all Dilution-Moria interaction breaks that effective time reversal symmetry. Some of them breaks. It depends on also the magnetic background or magnetic ground. And so we get a dispersion which used to be like this. Without that time reversal symmetry breaking, it becomes tilted at this point. And if I talk about only one state, then what is happening is that the parametric amplification amplifying at a point omega k as well as omega minus k. And this omega k and omega minus k is not equal to each other anymore. But before it was equal to each other because it was amplifying at k equals to 5 point. And that has a consequence. The field operator of magnons, which has only this part, which is e to the power I omega t by 2, now also have this extra oscillatory component, which is omega k minus omega minus k time t. And this Sx, the spin component Sx and Sy is superposition of many such oscillations. and many such magnons turn. So that is why it is giving a chaotic oscillation instead of a uniform oscillation. So we don't have any more a time crystal. So because the system becomes chaotic, and
So the system becomes chaotic.
yeah.
Is there a kind of relationship between up and down
Up and down.
spin channel?
Uh,
Because to start with, you had a ferromagnet.
yes, yes,
So
yes.
you had two separated spin channels.
Uh,
Now you have defined the magnon, which is excitation about this ground state. For example, you still have the Sx up and Sx down.
oh, sorry, sorry.
So there will be actually a difference between Sx
the
up
thing,
and down.
up and down means the eighth state. So I have considered a system which is kind of strip geometry, which is thermodynamic in this direction but has boundary in up and down. And
Why they will be
so this is the upside. So Sx up means the spin at the upside of the system, and Sx down means the
I think the top and bottom edge.
yeah, top and
Top
bottom.
and bottom edge.
Top and bottom edge. Yeah. So there are two edge states here, and both are corresponds to the top and bottom edges. So next, I have studied the stability against interaction of the system. So the interaction can be of different types. One can be of number non-conserving scattering process. Another can be number conserving scattering process. So in this slide, I have discussed about the non-conserving interaction. So although this does not conserve the number of magnon, but we still need to conserve the energy and momentum. And using studying the kinematics, we can answer how to reduce this interaction and to stabilize the system more. And I have plotted the two magnon density of state, which is expressed by this relation, and which means that, this is shown in this color spectrum. And these black lines here denotes the band structure. And when this color spectrum intersects with the black lines, the band structure, it means that at that point can decay into two other magnons in the band. Let's say this point, yeah.
still need?
Okay.
So the black lines are magnon band structure.
Yeah, band structure.
And what you are showing with the blue and with the shading?
Oh, the blue one, I am calculating decay over two magnon density of states. So the density of states, yeah. So that is.
And the color coding is with the amplitude.
Yes, yes. So there is a summation. So more so if I take 1 omega, and that omega if satisfies this relationship many times in the system, it means that part can decay into many possible ways. So that is amplitude. And so we can see that at Bz equals to 0 magnetic field, it overlaps with all the band structure. Whereas Bz equals to Js, it does not overlap below band structure because this two magnon density of states increases with magnetic field 2 times the magnetic field, whereas the magnon band structure rises up in energy proportional to the magnetic field. So if we apply magnetic field, then we can suppress this non-scattering process, and higher order magnon non-conserving process will go up more faster than this two magnon scattering process. So what about the stability in terms of the magnon conserving interaction? So I have two particle interaction term here, which I have derived using the Gaussian transformation, which is four particle interaction term, and it conserves the number of magnon. And I use this interaction Hamiltonian and calculated the Fermi scattering rate using Fermi's golden rule. and where I kept the initial state and so.
Basically, what are the kind of interactions? You have talked about two different kinds.
Yeah,
One
yeah.
is
Which
conserving and another is
non-conserving? Yeah.
what are the kind of
Oh, so the non-conserving terms can come from Division-Moore interaction. So and the conserving one can come from the Heisenberg interaction.
because if one has to physically, experimentally verify it.
Yeah.
So you are saying I should choose two different kinds of system?
No. So this is what I am talking about is the stability of the system against those interactions.
I understand.
Yeah.
But suppose I want to check your whatever is your hypothesis experimentally.
Yeah.
Then what should I do? You are saying I should choose in one case something which has some dominant Zaluzansky Moria and
Yeah.
some other material which has a centrosymmetric start with it.
No. It does not need to the lattice does not need to be centrosymmetric. Even without centrosymmetric, if I have Diagonal-Moria interaction, it does not mean that Diagonal-Moria interaction will break the effective time symmetry.
I understand that is
Yeah.
why I like to pinpoint because
Okay.
finally you have to connect to an experiment.
Yes. Actually, I have mentioned some materials and I studied that in my paper, but I have not mentioned in my slides.
But if you can say that, that will be useful because there are experiments.
Okay.
Volume is not here, I can see. Would like to test this.
Yeah. Okay. So yeah. Sorry about that. I missed that part. Yeah. I
So you are
mentioned.
saying it is just not Zaluzansky Moria. You have to see there are specific kind of Zaluzansky Moria.
Yeah, even if let's say I have a Diagonal interaction and I change the magnetic configuration such a way, let's say Diagonal is in plane and I have ferromagnetic ground state which is out of plane direction, then it does not break the so yeah, it depends. And also, let's say Diagonal interaction is out of plane, and if I have the spin
So you
configuration,
are saying if they are not really in the same direction, they are orthogonal, then they will not really.
yes. So, so this is the what I have calculated is the scattering rate here, and this scattering rate I have plotted against the delta E, which is the width of the energy level. So energy levels have some width, and that comes due to the interaction. It might come from the impurities in the system, or maybe magnon-magnon interaction, or maybe magnon-phonon interactions, and one can see the scattering rate is lowering down as the delta E, the width of the energy level is lowering down. And one can think, take the ideally the delta E to be 10⁻⁻⁶. And the corresponding scattering rate is 10⁻⁻⁸. And that denotes the 10⁻⁸ scattering rate per picosecond per lattice length, lattice constant, means that if I have a system of 1 micrometer, only one magnon is decaying per microsecond. So the decay rate is very small for this kind of system. And another stability is coming from the topological stability of the edge magnons, which are protected by the pi verifies of the system. And this pi verifies protection is shown to be robust in this PL paper, and which I am not discussing here further. And as a conclusion, what I have shown is that a time crystal made of topological edge states, which is protected by time reversal symmetry, and this time crystal has two requirements. One is the parametric amplification, another is topological edge states, and also it requires to have the time reversal symmetry. And these two ingredients here can be found in many bosonic systems, not only in the magnon system, but also can be found in the quasi-particles like phonons, plasmons, polaritons, or excitons. And so we propose that our scheme of making time crystal is also valid for other systems, bosonic systems as well. Thanks for your attention, and all my work is in this manuscript in the archive, and that is under review in the test journal. And if you like to have clarification, you can reach out freely using this email.
Thank you.
So thank you, Dhiman, for the nice talk and within time. So, are there any questions? We did have some discussion already during the talk. So, are there questions? Maybe from the students. There are a lot of students.
Hello.
Yeah. So, questions.
So let me ask the question. I mean, is there any kind of whole atom experiment?
Yeah. There are colorimetry methods that have shown the like Floquet.
So it is mostly on the cold atom system or
No.
solid state also?
Solid states also. Even magnons also have shown. So there are previously 3 papers. So there are 2 experimental papers and 1 is theoretical.
Maybe I would like to ask if this, what I understand is this correct.
Okay.
Yeah. So your way of saying that this forming a time crystal is that you have a response from your system whose frequency is lower than the frequency that you are driving the system. Is that the main take home message?
Yeah. Right.
Any more questions? Once again, students. Yeah. Okay, then if there are no questions, then let's thank Dhiman again for the very nice talk. And if any of you are here till what time?
Actually, here